This video is about work, energy and power. Now this is one of the most important areas in physics, and so questions about work, energy and power can be found in any topic. To the left you can see the equations. There are 6 equations I've presented here, but there are obviously far more than this. We can talk about the energy associated with heating an object, for example, but that's not included here because it is not included in B8. There are a few things to be aware of. When we say work done, we mean energy that is transferred. And so if you are calculating a change in energy of a body, then the change in energy is the work that is done. Now also in this equation for work done, you'll see it talks about displacement and force. The force and displacement have to be in the same direction for there to be the maximum amount of work done. If the force and displacement are perpendicular to each other, no work is done. We could rewrite the work done equation like this, where cosine of the angle between the force and displacement is multiplied by the force and displacement magnitudes. And this way you'll see that if the angle between them is 90 degrees, cosine of 90 degrees is 0, and so this equation gives 0. No work is done. But if the angle between them is 0, then cosine of 0 is 1, and so we get the maximum. You'll also notice that if the force and displacement are in opposite directions, then the work done is negative. Included next are 3 equations, one for gravitational potential energy, one for elastic potential energy, and one for kinetic energy. And these are just 3 examples of stores of energy. And if energy moves from one store to another, then work is done. The first equation for power is just the definition of power, the rate of doing work. In joules per second, 1 joule per second is equivalent to 1 watt. And the second equation for power here is what happens when you take the equation, the first equation for power, and you substitute for the equation for work done. So instead of W for work done, we substitute force multiplied by displacement. And as displacement divided by time is velocity, we arrive at the final equation. Now all 9 questions in section B8 can be answered with these 6 equations and carefully reading the question so that you understand what equations you need to apply. It is good to draw a diagram if necessary, but also it is important to check the units and make sure you're not being stung by any prefixes. Here's an example question. Let's say we had some unknown mass at the top of a ramp. The ramp is 2 meters long and inclined 20 degrees to the horizontal. And let us say that we release this mass and it rolls freely down this ramp. Let's treat this mass as a point mass, so all the mass is at the very center and there's no mass near the outside. It's a point volume. That makes the maths a little bit easier. And let's say we would like to know what speed the mass reaches the bottom of this ramp. Now it is possible to answer this question using mechanics and SUVAT, looking at the component of acceleration down the ramp and the displacement down the ramp, which is 2 meters, and calculating what the component of velocity parallel with the ramp would be. But you don't have to do that. You can use an energy argument. The mass will drop through a height of h as it falls. We know that all of the gravitational potential energy that the mass loses, it gains as kinetic energy because there's no rotational element of this mass to be concerned with. And that's because I said all the mass was at the very center, treating this as a point mass. If this was a volume, density uniform across that volume, as it rotated, it would gain rotational kinetic energy, but we're not going to include that here. So here is our equation, and we can cancel the mass, which is why that doesn't matter. So the speed the body will be moving when it reaches the bottom is a square root of 2gh. G is a constant, 9.81. H is what we need to find, and we can use trigonometry to do that. H is going to equal 2 meters multiplied by the sine of 20 degrees. Which is about 0.684 meters. This can then be substituted into the equation to find the speed, which is about 3.7 meters per second.